Okay, we have 2 more lectures. So today and Wednesday we'll focus on chemistry of alkynes. So they're pretty much the same thing as we learned already with alkenes, except they do it twice. So a couple more reactions today. We'll finish up on Wednesday, probably doing problem solving. You'll have your module 5 exam on Wednesday, your zip grade, and then your final exam next week, which is the ACS exam. So that's in person. Again, you're going to be here for that. I'll create a seating chart. So if you look at your seat, there's a number in front, and then the rows are letters. So I'll show your USMID along with seating assignment for the final. And then I'll use the photo roster and SOAR to make sure that it's you taking the exam and not someone you're paying to take the exam. So probably Thursday or Friday, I'll update the Canvas ABCD columns. That will include all your points for the entire semester, and then that'll give you a reflection of what you need to do on the final exam to obtain whatever letter grade you want. It's quite possible that you do go into the final with an A. That does not mean you're off the hook. You are required to take the final. That is a university policy. I'm not crossing my fingers. I swear to God, it's in the student handbook. It's in your best interest to take the final and do as well as you can on it. As I said, the raw score is about 20 out of 70. I think the highest score ever was like 68 out of 70. Not many students break the 60 barrier. It's quite possible to get 0 out of 70. That has happened. So again, do your best to prepare for that. Any questions? Yeah.
So next week we will not be on Monday, right?
Correct.
And we'll just have our exam.
So we're going to finish up the semester here with alkynes. And so alkynes are a carbon-carbon triple bond. Each carbon of the triple bond is sp hybridized, and so the geometry of that functional group is linear. So to summarize what we've learned so far about hydrocarbons, alkanes are fully saturated. We've used this molecular formula quite a bit, CnH2n plus 2, as a means to determine degrees of unsaturation. And if we follow the columns from left to right here, if you remove the element of molecular hydrogen, H2, so you're adding a degree of unsaturation that makes an alkene. So notice how the vocabulary changes. ANE to ENE, and then if you remove hydrogen again from that, you now have an alkyne, and so it's HN 2N minus 2, so there's 2 degrees of unsaturation. The most notable change in pKa is the acidity of the terminal, as we see down here, the terminal alkyne. That H has a pKa of 25. So it's fairly acidic. It can be deprotonated to form a carbanion. The other type of alkyne is internal, where R1 and R2 are both carbon. So as you would assume, the bond length decreases from alkane to alkene to alkyne. You're putting more electron density between the 2 carbon atoms, and so these have the shortest bond distance of 1.20 angstroms. So angstrom is, again, 10 to the minus 10 meters. You'll notice that the bond energy increases. So you have a sigma bond, sigma plus pi, and then sigma plus pi plus pi. And so this column here shows you the sigma bond, pi bond, and pi bond. So notice that pi bonds are much easier to break. That's why they do the addition reactions. So here's a cheap drawing of what those two pi bonds look like. So remember that a pi bond consists of two p orbitals that are overlapping on both lobes. So in say the red plane, which is in the plane of the whiteboard, you have one pi bond, and then in the blue plane, which is orthogonal to that, so that means 90 degrees, is the other pi bond. So they sit orthogonal 90 degrees to one another, and it's quite a bit of electron density between those two carbons. And so they will basically undergo double electrophilic addition. So remember that we're treating with some electrophile, say AB, and then the alkyne is the nucleophile. So that supplies electrons. So the naming is pretty straightforward. You take the basic alkane name and you change the A to Y, so that gets you alkyne. So here's your carbon count going down the first column. The second column tells you if it's terminal or internal. And so there's the name ethyne, so C2H2. Notice that when we get to 4 carbons, now we can have the isomers where it's terminal or internal. If it's internal, you then have to specify the starting carbon of the triple bond. So 5 carbons basically has 2, 6 carbons 3. As you increase the carbon count, that number will increase as well because you're moving the triple bond more internally. So ethyne is commonly called acetylene. So acetylene gas, because it's a terminal alkyne, those CHs are acidic and they can be deprotonated. So you can make any alkyne from acetylene. So for example, let's just pick on this one right here. So we can see the triple bond. That can essentially come from acetylene. And then we can make these bonds that I'm dissecting here to be whatever carbon length plus a leaving group. So that's SN2 chemistry. The acetylide anion is the nucleophile, and then you're reacting with an electrophilic partner to put the rest of that side chain on. So this table adds some more columns to show you how you would do that, starting from acetylene. So typically, you have to use a pretty strong base. I'm just going to write B. So that base will abstract a proton. So you lose the conjugate acid of that, and then that generates the acetylide anion in whatever metal was associated with that base. And then, as you would see from chain length 3, the electrophile that you would use is just methyl bromide. So because it's SN2, you still have to follow that trend. Methyl greater than primary, greater than secondary. So if you have a tertiary carbon next to that acetylene, you really can't use this chemistry to make that. But the E1, or electrophile 1 and electrophile 2, show you the partners that you would need to take acetylene to that alkyne. So one aspect of alkynes that are important is the heat of combustion. And so really what this slide is showing is that if you want to cut metal with fire, the easiest way to do that is with an oxygen acetylene mixture. So that's an oxyacetylene torch. And so that will get hot enough to cut through metal. So nowadays, more refined methods use high pressure water or plasma. So there's these CAD, computer-aided design machines. You put a thing in and you can cut metal to basically any shape you want. But basically, the reason that the alkyne is the best hydrocarbon to do that is shown in the table here with some numbers. So a combustion reaction takes your hydrocarbon plus oxygen plus a spark or fire to get the combustion going. And so for the C2 hydrocarbons, you can see the structures here. The moles of oxygen that balance the equation are shown. So you get CO2 produced, water produced, and then the heat. And if we look at, they're all producing 2 moles of CO2 because we're starting with 2 carbons. They produce different amounts of water. So notice that acetylene produces only 1. And then the final column is just adding those numbers together to get the total moles of product. The heat evolved in this column. So that's measured experimentally. So if you take that number and divide it by the number of moles of product, you get the number in the last column. So what it's basically telling us is that as we go from alkane to alkene to alkyne, that produces the most heat. It's the most efficient in the combustion reaction. So it'll allow the torch to get hot enough to melt through whatever metal you're dealing with. So combustion is obviously an important reaction. The mechanism of it's pretty complex. We won't talk too much more about that other than it's benefited society greatly. So we'll go over the alkyne addition reactions now, and then we'll do some synthesis problems to wrap up today's lecture. So we know that there's pi bond, and then they're held together by the sigma bond. So you can fully hydrogenate an alkyne to an alkane using hydrogen gas. And so this is typically, if you're doing it at atmospheric pressure, so 1 atmosphere, you just get a balloon, you fill it with hydrogen gas, and you bubble it through. That tends to take quite a long time. So you can increase the pressure. So I'll write up arrow P. Using a stainless steel vessel. And when I say stainless steel, I mean like when you put the cap on this thing, you got to screw it down with bolts because the pressure is pretty high so it doesn't explode. You also need a metal catalyst, and so this is typically a transition metal such as platinum, palladium, or nickel. And then based on the mechanism, the solvent has to be polar and protic. And as you see, it adds 2 equivalents of hydrogen across the triple bond. So the hydrogenation reaction is one way in which degrees of unsaturation is figured out experimentally. So it's called the uptake of hydrogen gas, and basically you use the ideal gas law, Pivnert, rearrange for N, and then just using the gas gauge on the tank, you can measure how much pressure was put in, what's the decrease, and then figure out the moles. So again, that's degrees of unsaturation, where we use that CnH2n+2 exercise throughout the semester. So that's called total hydrogenation. So there are methods that will partially reduce a triple bond. And so these two methods do it in very specific fashion. The first one takes an alkyne and generates a cis alkene. And the difference here really is there is an additive that's called a poison. So one poison is called quinoline. And essentially what it does is it stops the reduction after 1 equivalent of hydrogen has been taken up. So these conditions will not go to the alkane. So we get the cis geometry, and then we can prove that by NMR because that coupling constant will be about 13 hertz. The hydrogenation mechanism, again, it's pretty complicated, so I'm not going to attempt to even explain it. The reason the metal is there is that the metal will associate with the H2 on the surface. It'll split the HH bond, and then the alkyne comes along, and then the metal gives those hydrogen atoms back. So another type of reaction, this is technically called a reduction, even though you're adding hydrogen across the triple bond. So now the alkane goes to the trans-alkene. So trans geometry. And that coupling is going to be slightly larger at 15 hertz. Notice the conditions for this are quite different. It uses sodium metal, and the solvent is ammonia. So see the H there in red? The hydrogens come from ammonia. And this is called the dissolving metal reduction. So sodium metal, if you've never seen it, it's sold in like cubes that are about 1 centimeter in length, width, and height. So you can cut it with a butter knife, and the surface is nice and silvery, shiny. And then you add it to the ammonia, and then you'll see it eventually dissolve, and the ammonia will turn like a deep blue color. So what's happening is sodium is giving up an electron. So the ammonia is solvating that electron, which gives it that nice deep color. And so on the next slide, I'll show you a little bit about how that happens and why you end up with the trans geometry specifically. Ammonia is typically a gas, so it condenses at minus 33 degrees. So basically you get a flask, you cool it colder than that, you can condense the ammonia in it to get a liquid that looks like water. It's water white, as they say. You add the sodium, and then you add your alkyne. And so I wrote sodium, this little thing here, it's called naught. So sodium 0. It has that extra electron which it wants to donate. So it's going to donate it to the triple bond. So I'm just going to write Na in that electron. So it'll donate 1 electron, and then we'll break the pi bond. So notice that's now a double-headed arrow. So I'm using that word vinylic, and that's important because that's telling you that either the lone pair or the radical reside in an sp2 hybrid orbital. And so based on the way that adds, that sets up the trans geometry. So you have a vinylic carbanion that's pretty unhappy. So it's going to react with the ammonia to protonate it. And now you still have that radical, so another equivalent of the sodium will add the second electron there. And then that will react with ammonia again. And that will give you your trans geometry. Any questions? Yeah.
The nitrile was, I guess, terminal, or would there still be trains?
It would not, because that terminal carbon would have 2 hydrogens on it at that point. So there's total hydrogenation, partial hydrogenation, either the cis or trans geometry. And now the rest of the reactions are conditions we've seen with alkenes. So the first one, we're going to treat with 1 molar equivalent of bromine in a non-participating solvent, dichloromethane. And so this will give you the trans dibromide. If you have an excess of bromine, that alkene now just behaves as we've seen before. So it'll add that Br2, and now you've added 4 bromine atoms across that triple bond. So these polyhalogenated alkanes have unique chemical and physical properties. So one of them is that they're used as fire retardants, so you can stick them into clothing and stuff like that to reduce heat exposure. So other things, they're lubricants, plasticizers, additives, sealants, and adhesives. So those are all materials that we use in civilization, but for every good, there's a bad. So the yin and yang of life here. They're persistent organic pollutants, or POP. And so what that means is, everything eventually will leach into the environment and get into the water table. And there's really no organisms that can digest these things. So for a lot of things, there's organisms that will chew it up, make it biodegradable. But for these, those don't exist, so they hang around in the environment and they do bad stuff. So for every good, there's a bad, basically. If you go on to take, say, medicinal chemistry or pharmacology or toxicology, you'll learn about, when you have a prescription and you don't take it all, what's the first thing you do as a human? Either keep it till you're sick again, or if you don't want it in your cabinet, you throw it away how? Flush it down the toilet. So what's bad about that is it ends up basically back in the water table. And, people that do environmental studies can sample things, and, they'll find prescription drug residues in community water towers and whatnot. So if you do have any, take it back to the pharmacist and let them throw it down the toilet, whatever they're going to do with it. So the next reaction, I've given you sort of a canned substrate here that makes it a little bit easy to determine. We're starting with a terminal alkyne. And we're going to add HCl. So this follows Markovnikov's rule. you see that the terminal carbon already has an H. When you add the first equivalent of HCl, that terminal carbon gets the H. The internal carbon gets the chlorine. And then if you add an excess, it still obeys Markovnikov's rule. And then you get this geminal. So geminal means 1,1 dichloride. What can be more complicated is if you have an internal alkyne that's, say, non-symmetric. So HCl in excess. What's hard about this is, determining what carbon's going to get the H first. There's nothing really to differentiate either end, so you're going to get a mixture of things here. So the HCl, those two different elements can add either way. There's really nothing that is going to control that. Yep.
Will there be a preferred option? I think the question was asking about which one it was produced. Is there one that's preferred of those two?
So the question was, is there a preferred or major product? If there is, I don't know the reasoning. What you should be able to do is just figure out how many total products there can be. So I think this is the last reaction here. So oxidative cleavage with ozone. So ozone gas. What's unique about alkynes now is that no matter what, you're always going to end up with a carboxylic acid. So the two carbons of the alkyne are highlighted by those red dots. Basically, you clip between them, and then each of those carbons becomes a carboxylic acid. So that's the theory of it. In reality, would you want to run this exact reaction? Probably not, because it's producing two different carboxylic acids. Their boiling points are probably very similar, so they'd be hard to separate. So ideally, if you were to do this, you'd want the alkyne to be symmetric so that you're producing two equivalents of the same molecule. Yes, it is. So we'll do a couple questions, and then we'll get to a synthesis slide or two. So if we wanted to take 3-hexyne to trans 3-hexene, what conditions would we use? So the trans geometry comes from the dissolving metal reduction. So that would be C. If we wanted to make the cis alkene, we have to use the poison. And so that poison is quinoline, or I think your book may use barium sulfate. And then finally, total hydrogenation would use conditions D, where you have the hydrogen gas, platinum metal, and methanol. Anyone ever steal a catalytic converter? So do you know why they steal them? Huh? It's the metal in it. It's typically palladium or platinum. So you can strip the metal out of that. So when your engine combusts stuff, you have those gases going through, and we like to breathe clean air. So that gas goes through the catalytic converter, and it's basically producing CO2 and water to scrub out the more toxic gases that are produced from combustion. So you can, if you've donated your quota of blood and they won't accept any more this month, you can go steal some catalytic converters. So the reason, again, people steal them is because those metals are pretty expensive. If you're into the stock market, look up the price of gold, platinum, palladium, and you can make a decent buck now and then. So the question was, what do conditions A do? Those will do hydration. I didn't talk about that one in terms of a reaction because, again, when you get to the internal, it gets a little bit more complicated about what it's going to do. But it'll do hydration just like an alkene will. So here we want to make an alkyne starting from acetylene. Yep.
On that previous slide, what we generated from the conditions.
So it says we're starting with acetylene, and then we want to go sequential SN2 reactions, where we use 2-bromo propane and then ethyl bromide. And so what would the alkyne be? So again, the base will deprotonate each H. Then we're adding those electrophiles, so we'll just redraw the alkyne. So the one side gets an isopropyl group, the other side gets an ethyl group. So I think we want to number it starting on the right. 1, 2, 3, 4, 5, 6. So that's going to be a 3-hexyne. And then at position 2 is a methyl group, so that's going to give us B as the correct answer. So here it's asking, after ozonolysis of that alkyne, what carboxylic acids are produced. So again, we're going to clip here. So we have 1, 2, 3 carbons. that third carbon becomes the acid. So we'll just say 4, 5, 6. So carbon 4, 5, and 6. 4 becomes the acid, so that's 3 carbon propanoic acid. And then 2 methyl propanoic acid. So that looks like it's A. So put another way, what starting alkyne would give you 2 equivalents of ethanoic acid? So if we're thinking backwards, I'll draw the other equivalent. So we basically need to stitch these two together with a triple bond. And so that would give us 2-butyne. Any questions? So this type of problem is called a starburst scheme. And so we're starting from the middle functional group, and then we're basically applying all the reactions that you've learned for that functional group. So some of them we supply the reagent, most of them we predict the product. So we're starting with phenylacetylene. So a terminal alkyne, it's not symmetric. We'll say up here in the first conditions with hydrogen gas, palladium, and methanol, that's going to do total hydrogenation. So that'll produce ethyl benzene. Maybe one thing I can point out, so as I highlighted in red there, like nothing's happening there. So in blue, that's where the action is happening. And so as you prepare for the final exam, that's really what you need to focus on, is what functional groups do these reagents act upon? Because you don't want to be doing something in another part of the molecule that's not even relevant. So with excess chlorine, each carbon atom is going to get 2 chlorines. And so that makes the tetrachloride. For conditions 3, we have to supply the reagents. So we look at how does the starting material change to the product. And what's happening is that H is being substituted for 3 carbon atoms. So we would use a base like sodium amide, and then a 3-carbon electrophile such as propyl iodide. And that's an SN2 reaction. So going down from that product to conditions 4, we have dissolving metal. So that'll make a trans alkene. And then conditions 5, use bromine with a non-participating solvent. So now we're going to end up with the vicinal dibromide, but that trans geometry is retained. So I'm going to draw the bromines in first. And then I'll put some stereochemistry in here. So H, the propyl, H forward, and then the benzene ring back. So not only do you have to remember what those conditions do, but a little bit of the mechanism as well, so that you know it's the trans dibromide, because one bromine adds, then the other one adds from the other face. Condition 6, we're taking the starting material and then we're making this geminal dibromide. We see that that terminal carbon goes from 1H to 2 H's, the internal carbon's getting bromine. So we would use an excess of HBr. Condition 7 are oxidative cleavage. So we slice through the alkyne. We would end up with benzoic acid and then formic acid. So formic acid is what stings you when you walk through the ant pile. The little ant injects formic acid into your skin, and that's what burns. Benzoic acid, the sodium salt of that, is used as a food preservative. So if you look at your Wonder Bread or Bunny Bread or whatever bread you eat, there's probably benzoic acid in there as a food preservative. And then rounding out the trip here, conditions 8, we're going from a terminal alkyne, even though it doesn't look like it, it's forming a cis alkene. It's done a partial reduction. So this would be H2 gas, the quinoline, poison, and the transition metal. So I'm calling it cis, even though there's one substituent, just to highlight the fact that it's a partial reduction. And then treating that with HBr will obey Markovnikov's rule. And we'll get the secondary bromide. Any questions? So we have enough time to do another one that I made up. Just looking at your textbook here. This one starts with an alkene, and R is basically anything the other part of the molecule. Really what we're focused on is just the chemistry of the double bond. So these are going to be addition reactions as a review. And then just keep in mind the product you form, you can generate a star burst from that to review the reactions that we've learned this semester. So if we wanted to take the alkyne and go to the secondary bromide, we just saw that we would use HBr. If you wanted to go back to the alkene, this would be a Zaitsev elimination. So we want to form the least substituted alkene, so we would use a small base, say sodium ethoxide in ethanol. So these terms, Markovnikov, Zaitsev, Hoffman, they should trigger some memory in terms of what type of product is going to be formed. So notice now in conditions 3, we're forming a primary bromide. So I'll draw the other element H there. We can't use HBr because that is going to form the more substituted bromide. So back from module 4, we learned about using HBr with peroxide. So notice the difference here. The presence of that peroxide with the HBr switches the regiochemical outcome of where the bromine adds. So moving from the primary bromide to the nitrile, that's a functional group transformation. So it's substitution of Br for Cn. So that's an SN2 reaction. We could use potassium cyanide and say acetone at 60 degrees. And the other thing to keep in mind is, as we're going through this, how do you identify the functional groups that are then present? So cyanides have that triple bond stretch around 2200 in the IR. Again, bromine would use mass spec. You'd have a 1-to-1 ratio of the parent to the parent plus 2 ions. Conditions 5 here. That's hydrogenation of an alkene to an alkane. So H2 gas, palladium metal on carbon in methanol. Six is forming a primary alcohol. So a lesser substituted alcohol comes from hydroboration with borane. So BH3 and then work up with sodium hydroperoxide. Gets you the less substituted alcohol. Since that's a bad leaving group, we can transform it into a good one using tosyl chloride in pyridine. So now we have a good leaving group. Conditions 8. That's a 1,2 diol. So this would be osmium tetroxide. Nine is an epoxide. So that's MCPBA. Ten is a halohydrin. So this would be bromine and water. So notice there, the water is a participating solvent, meaning that you see some of the elements incorporated into the product. So a halohydrin you can treat with a base, say sodium hydride and THF. That deprotonates the alcohol, which then attacks the carbon bearing the bromine, and you can make an epoxide that way. And then finally, 11, we see a vicinal. So vicinal again is 1,2 dibromide. Notice now that's going to use bromine, but the solvent has to be non-participating, so dichloromethane. So you might even run that in lab. You get some alkene, you drip in the bromine, and so that bromine color goes away. That's a test for the alkene. When you see excess color, that means you've completed the reaction. So that's going to wrap up today's lecture. On Wednesday, we'll probably do more of this stuff. I'll just bring the book along and we'll run through problems as a review. So you have a quiz today, a quiz and exam Wednesday. That's the last lecture, and then your final next week.